Okay, the next speaker is Carlos Mastalli. Carlos is a research associate in the University of Edinburgh and Alan Turing Institute. He leads the steering committee of Crocodyle, which is a software I think he's going to talk about today. He did his PhD in IIT, working on the robot IQ, locomotion on challenging terrain. He does research on different aspects of especially legged locomotion. Yeah, I think we are looking forward to your talk, Carlos.
Hello, everybody. Thank you, Majid, for the introduction. Thank you, both of you, Majid and Farbo, for the invitation. I'm delighted to be here, and I hope this talk is going to be interesting for many of the persons in the audience. Yes, today I'm going to talk about Crocodyle. I'm going to talk about recent progress on predictive control and codesign based on Crocodyle. But before going into, a boring, talk about many equations, I would like to show you some of the results of Crocodyle. So this motion is Crocodyle is able to compute this motion based on a set of predefined behaviors. So here the behaviors that you see are graph the bar in a given time, be in this vertical posture, and after in another given time, down in a specific posture. The rest of the motion, like crossing the legs, the swimming, are motion generated for first principle of optimization. So I haven't put any hint, any clue, any heuristic to make those motion possible, of course. You can see that this Crocodyle is optimized, it's using the full dynamics, it's optimizing, it includes the torque limits, joint position limit, joint velocity limit, friction constraints. So pretty much is handling many of the common constraints and models that we use in like a robotics, but also in other fields. I also would like to show you some of these results that, these are like a few months, a couple of months ago results on the animal robots. So what you can see here is we have translated these, ways of generating agile motion into the animal robot, the animal B. So here it's a model predictive control algorithm running at 50 Hz, considering the full dynamics, the torque limits, the joint limits, pretty much as the previous video. What you can see here, it's animal jumping 25 centimeters forward. It can also jump laterally. The height is 15 centimeters. Some of these results are possible using our full dynamics model predictive control algorithm that I will describe in this talk. So let me, I have prepared for this talk the following, points. So first, I would like to start discussing about the benefits of the full dynamics and prediction. It might be obvious. You might have an obvious answer, but what I've seen among folks in my field, some of them might have like naive answers why we should use full dynamics. So I would like to show a perspective why I think we need full dynamics, not just because we want to, capture all the dynamics of the rigid body dynamics of the system, but also because there are some messages that the full dynamics is telling out in rigid body system. Then I want to do a brief introduction of Crocodyle, which is the library that is generating all this motion. Crocodyle stands from Contact Robot Optimal Control by Differential Dynamic Library. So it's basically telling the policy, what is the scope of this, this library. Later, I would like to do to introduce some basic concepts of differential dynamic programming that we use in our daily basis research and also in the library. And make some connection with nonlinear programming because yes, DDP is not a different algorithm, it's another NLP, it's a way of solving NLP problems for optimal control, of course. And also I want to talk about the content dynamics that with the perspective of trajectory optimization and optimal control. I know that just I have introduced a bit about this content dynamic, but I want to show you why they are also interesting for us in Crocodyle. Later, I want to describe briefly our hybrid predictive control algorithm, show you some results, show you different ways that we can control this robot and the implication of that. And finally, I want to conclude this talk with some project that I'm working on codesign. So codesign aims for designing the robot. So the length of the limb, the payload distribution, the mass of the trunk, the motor dimension from first principle of optimization. At the same time, it aims to not only find an optimal design, but also find an optimal trajectory. So this leads with new ways of designing robots that might, in future, be able to generate any kind of behavior. Which I'm pretty interested and excited to work. So let me start with the full dynamics. Of course, full dynamics. If you use a reduced model, let's say single rigid body dynamics, or you use inverted pendulum, those models are capturing quite a lot the dynamics of a legged robot, but they are neglecting many things, and it's not just about the full kinematics or about the way of imposing torque limit, but also about the way that rigid body systems are, the nature of this system. And I want to say that the nature is related with this concept of non-holonomic. I like it to call non-holonomic motor intelligence. And this concept was introduced by Bieber in his work. So basically, when in a rigid body system, when we want to conserve the angular momenta, if you analyze the equation of the angular momentum conservation for a rigid body system like this cat, you will see that it imposes non-holonomic constraints. So, for instance, to be able to generate this cat motion, what we need to do is to, in terms of physics, is to conserve the angular momentum. What the cats need to do is to figure out a motion that is conserving the angular momentum, which in this case is rotating his front and hind parts in such a way that conserves the angular momentum. But the problem of the challenge of this, it is not a trivial way. I mean, there's not a trivial way of solving this because there's a non-holonomic in the system dynamics. But what is this non-holonomic thing? Well, when I think about non-holonomics, that the first thing that comes to my mind is this car parking problem. So what you can see here is we want to park our car in a given position from a starting point, let's say from A to B. But this is not possible with an instantaneous action, as the car cannot move laterally. It's because a car is a non-holonomical system, and you can indeed reach any configuration point, but not with any possible path. That's exactly what is happening in the cat. So if we want to control or generate this kind of motion on a cat, or like a quadruped robot like a cat, so we need to consider the full dynamics, because we have to guarantee the angular momentum conservation in this motion, and there is not a way to do this with the state-of-the-art models using like reduced dynamics. Why is this important? Is because we want to develop methods that can generate any kind of motion in any kind of robot, right? Not only legged robots. So another in the community, what is typically done is, well, you say I use a reduced dynamic that captures my motion, so I plan my motion based on that. But later I will use a controller that encodes the full dynamic to resolve some of the aspects that we were not able to handle in the motion planner. And this whole body controller, or TSID, is what indeed Andrea has presented today. But the problem is the system is non-holonomical, which is mean that we need to plan ahead as we do with a car for parking in a specific place. So we need to also consider the full dynamics at the motion planning level, not only at the control and execution. That leads to a way of solving this, very classical mathematical, is through the framework of optimal control. But we need to consider the full dynamics of the system. What we have done here in this video is to study indeed this kind of motion, and we with our algorithm, we generate a motion where the HRP2 can change its attitudes while keeping the angular momenta constant. And this is possible because there is a coordination between the two legs in such a way that we cancel the angular momenta. And again, this is a, it's a changes of attitude in like an astronaut, because there's not a gravitational field here. We have to remove it. But you might say, oh, why I need this? Because my robot is not doing that. It just needs to walk. But actually, the benefit of the full dynamics go beyond just attitude, momentum control, but also it helps to, for instance, to generate this walking pattern. In short, this walking pattern won't be possible with a reduced dynamic, and let me explain you why. So might look easy walking pattern, but indeed, this walking pattern is reaching the limits of the HRP2 robot. So this is a 1 meter stride walking pattern, and the way that we can, I mean, the way that because we use the full dynamics, what is happening is the optimization algorithm, it's realizing that we can move these swings in, like you can see here, so in such a way that we reduce the ground reaction forces in the left, and eventually the torques that we need to supply to the joints. And again, this won't be possible with a reduced dynamic model where we are not capturing, the nature of like move the swing arm motion. So the benefits go beyond attitude regulation. It allows our robots to reach their maximum capabilities, right? And this is the starting point of Crocoddyl. We did this for motion planning at that time, but we were interested in looking ways how to scale this into reactive motion planning, predictive control, because the nature of robot is, they are working in a dynamic environment, they have to be reactive. And that was the motivation of building Crocodyle. Crocodyle is an open source project. It uses BS3 license, so you can use it for anything. We are building a community. We are very happy to receive your issues, questions, and also pull requests. Why not? Some of the silent features of Crocodyle supports code generation and multi-threading. It indeed helps a lot in the computation time. It uses analytical derivative. You can also use automatic derivative. This also is, as you have seen in the Justine talk, is also a very important ingredient for scaling this algorithm to the level we need. It has also Python bindings, which allows you to develop new models, new solvers, and indeed we are using this in our daily basis research. So it's quite useful. Perhaps Crocodyle is the main core technological development of the MEMO project. MEMO is an European project which I belong, and it's some from Memory of Motion. And these are some of the partners that in the MEMO that are using our software and developing new research work on that. Here in UK, we have the University of Edinburgh, and where I am, of course, but also at the University of Oxford. In France, we have Invias, UNRS, Caesar Lab, IDEA. In Germany, Max Planck Institute, also in the University of Trento in Italy. But to be honest, there are many other users out there that I'm not aware of. We're happy with how our community is growing. These are some of the works that have been possible thanks to Crocodyle. So you can see all of them. These are predictive control algorithms that are going to higher frequency from 100 even to I think 300 hertz, depending on the video. So you can see that, for instance, Crocodyle controls the talus human robot to avoid obstacle in manipulation times. You can see some work on including reduced dynamics in Crocodyle and using our FTDP solver, which I will present to deal with this locomotion gate on the solar robot, and also to improve the compliance on manipulators, as you can see in the last video. But there are many other works that also I'm involved with. So, for instance, the codesign, which I'm gonna explain in this talk. But again, as I mentioned, what we want to do here is optimize motion, optimize a robot design. Also, there's people at CICIT in Barcelona with some collaboration with NASA GPL, where they are working in a real manipulation. They have done this simulation, and they are in their process to make this in predictive control. So also in the FKI in Germany, they have been using our solver to validate some of the design that they are doing on this humanoid robot, but I think they are also using other projects as well. So I like to think that Crocoddyl is enabling athletic motor skills. Yeah, I want to say this with a humble, with my saying, although that sounds very, very strong, but this is how I like to think what is doing Crocoddyl. So I'm particular and completely fully motivated to generate this kind of motions on robots. So having humanoids that can do athletic gymnastic routine, quadrupeds that can jump, do agile, precise, aggressive motions. And this of course will be important because it will enable capabilities to the robots of the future. We in Crocoddyl are using the full dynamics you might get, but there are some essentials for in Crocoddyl. So I like to classify this into behavioral and motion intelligence. So what is doing Crocoddyl at the moment is solving all the motion intelligence. What is motion intelligence? It's just a continuous process where you want to connect from one behavior to another while guarantee the physical realism, the feasibility of the motion in terms of actuation and so on. And what are the behaviors? A set of, you might think as integer variable, high level behavior where they tell you, well, grab this bar, then balance there, and then landing. So they are high level behaviors that are, in my humble opinion, more related with environmental condition and with a global task that goes beyond to what is motion intelligence, in my perspective. So here I want to describe briefly some basic aspects of differentiable dynamic programming. They are not, this slide are not the classical DDP algorithms because I think they are lacking of some of the nice features that we can see in NLP nonlinear programs. And actually I want to do a connection with nonlinear programming. So let me first start describing this nonlinear optimal control problem in general. What we want to do, this is a direct restriction. So what we want to do is to optimize a set of trajectories in the space. So these are these S. What we want also to optimize or to compute is a set of controls, US. We want to do this to minimize a cost function or a set of cost function along a horizon end. These are these L functions. We want to do this by ensuring some physical realism, like the dynamics of the system and also initial state. Of course, there are more constraints that you can put. Typically, you need to do it, but for the sake of simplicity of my presentation, I'm just gonna be ignore them. But to be honest, what the set of this problem is, it's yet another NLP problem, and you can see it as from that perspective. So what a nonlinear programming is trying to do is to find a KKT point, so to satisfy the first order optimality conditions. How you do this is recursively by the application of the Newton method. What it's interesting in the problem of optimal control in particular is we can focus on one specific node. So you might see that this, the transition from the node K to the node K plus one, so depends only on the previous state. So we say that this is a Markovian transition. We might also say, I like also to say that there is a temporal structure in the problem. And this is something that it's particularly applicable for optimal control problems and not generally applicable for NLP. That's why we can do further optimizations to scale these algorithms to the level that we need. When we apply the Newton method to the KKT condition basically, and we focus only on one node in the computational graph, we get this system of equation that we need to factorize. So here you can identify some of the aspects. So this delta H and delta U are, so the improvement, let's say, towards a local minimal on the primal variable. So the trajectory of the state, well, in this case, the state of that node and the control of that node. Also, delta S prime it's for the, you know, the next node. And the lambda plus is actually lambda is equals to lambda plus delta lambda, which is basically the new value of the augmented Lagrangian for the equality constraint that defines this dynamic equation. Another thing that you might observe, the two first rows describe what is the, I mean, the so-called stationary condition of the KKT. I mean, that are part of the KKT condition. And these are, I mean, these are that you can see here. Well, we can see that in the left matrix we have you know, the Hessian of the cost function, which are these LHS, LHU, and so on. The Jacobian of the dynamic, which is Fx and Fu. The gradient of the cost function in the other side of the equation. Another interesting point is the third row. So that is a primal condition that is eventually going to guarantee that the dynamics are going to be hold. I mean, the solution that is going to hold the dynamics is going to be physical. It's going to be possible in terms of physics. But a key observation here is we have this F bar, which basically is measuring at that node, at that specific iteration, the infeasibility of the dynamics. So in theory, what we want to, I mean, convergent, what we will have is that value will be 0. And that's the assumption that differentiable dynamic programming is doing. It's every time iterating through a feasible solution, which it is not really good in terms of numbers, although that might sound reasonable for controlling a robot. It is not reasonable for solving this kind of problem. And this comes from, you know, making this relationship with nonlinear programming. Another thing is this last row, which is might be a bit more obscure for many of the other, but I won't be fully clear at the moment. I need to elaborate a bit this slide, but so what is doing this row is connecting the specific K node with the K node, the next node, which is the K plus 1 node. And this connection is through this approximation of the value function, which is you know, the gradient of the value function Bx and the Hessian Bx. And we will see how this connects. So bear with me in this slide for a moment. So what is doing DDP? If we try to understand DDP a bit more, it's basically solving a larger problem into a sequence of smaller problems, like you can see in the right equation. These are the smaller problems, because we are solving one problem per node instead of solving the whole trajectory. So if you want to see the entire problem, so more or less the sparsity pattern, it's something like you can see in the last picture. It's a banded, it has a banded structure, and this is due to again the temporal structure, the Markovian relationship that are between nodes. And what is typically doing NLPs of the shell NLPs is solving this, factorizing this matrix through the using a sparse solver. But it turned out that we can compute this without exploiting using a sparsity solver, and lever further optimization, because now we have matrices that are smaller and fit into the cache of memory, and in general is way more faster. So what is a typical operation? If you see the right equation, what we can do is to condense the bottom two rows. And condensing means to put it in a system that is reduced, but it still is the same thing of equation that before. And this is again similar to the equation of DDP, but now we have these returns that are not considered by DDP. And again, you can see this as a DDP because if I write the equation like this, these are the typical approximation of the Hamiltonian that we see in the, like in Wikipedia page of DDP. What we are doing is, because we can, at this moment, see a relationship with the Pontryagin principle, we can actually solve this problem and get the delta U. So, which is basically a combination of the feed-forward term, this small k, and the feedback gain, which is this capital K. Another thing that you want to see is now we don't have to factorize the bigger a problem for the K node, the first set of equation. What we really need to factorize is QUU, only QUU. And this leads to like the most compact problem to be solved for a specific node. So that's why TDP is leveraging the sparsity, condensing the problem, reducing the problem, and solving the minimal problem, like let's say in the minimal coordinates. And actually, this is the basis of the recursive recursion that we use in many algorithms, like OLQR algorithms or Kalman filters. But from the point of view of a mathematician developing nonlinear programs, you can see that our recursive recursion is just computing a certain direction, and this might not be an obvious concept when we are reading literature, because there's lack of connection in the textbook with nonlinear programs and recursive recursion. Also, in terms of complexity, what we see is instead of solving this large problem and using an sparse solver like off-the-shelf solvers, because we don't know the structure. I mean, you cannot assume the structure in a general proposed nonlinear program. So you can see that the complexity of factorizing is qubit. So it means that this qubit with respect to n, which is the horizon, and m, the system dimension. So the dimension of the stasis and control. And now with the recursive recursion, it approximates to the complexity is linear with respect to the horizon, and the only thing that remains qubit is the system dimension, approximately. This is an approximation of the algorithm complexity. So this leads with an important boost on computation time, because the most expensive thing to do in optimization is to compute the third direction. That's the most expensive procedure, because you need derivative, and derivatives are expensive, but also computing the third direction is expensive as well. And as you see, I have presented DDP with this test that considers the feasibility, but that's not really the classical DDP. I decided to do it in that way to make a smooth introduction to this feasibility-driven search algorithm that we developed. The algorithm is, again, I'm not going into any nitty-gritty aspect of the algorithm, but it's, again, inspired on direct transcription. I have this diagram here that I prepared to a bit explain from a high-level point of view how it works DDP and how it works our FTDP. So DDP, as I said before, is iterating through feasible trajectories. It means that it's moving along this wide course that represent the constraints of the dynamics. It's also computing a certain direction along that, because the system is non-linear, and the third direction is computing based on a non-linear approach, in a local approximation. It turned out that in practice, when you do so, you cannot apply larger steps, so you cannot do bigger bit motions towards going to the local minima in this cost landscape blue. Instead, our feasibility-driven DDP, because allows this feasibility, in practice means we have iterations that are larger and converge eventually within fewer iterations. Another thing is DDP can be easily stuck in local minima if you are still moving this feasibility domain, let's say. That's not very convenient, and that's why many people in the community say, well, DDP, it's not really good algorithm. It's stuck in local minima, but I think it's not really the truth. The truth is the classical DDP is really bad, but you can take some of the good advantages and do it better. Our FTDP solver can be one star with the state and control. So it's a very nice feature, and let me explain you why. So DDP, you only one star with the control, and then you have to roll out. You need to simulate your equation to get the state trajectory that it's indeed feasible, right? So small changes in the control, of course, leads to big changes in the motion of the system, because there are some significant sensibility in the problem. And that is not really desirable, especially when you are doing a very aggressive motion like jumping. That's why you prefer to, instead of one start the control, to one start the state, or both. Because if you do a simulation and let's say diverge or it's close into diverging because some small deviation in the control, then you start to do iterations through a trajectory that is pretty bad. And these are the problems that we can solve with Crocoddyl. All these problems that you see here are being solved within 10 to 30 iterations. Each iteration, depending on your computer, but it might take like 10 milliseconds. So solving the whole problem might take 100 milliseconds to, I don't know, 500 milliseconds, half of the second. So which is quite good because it tells us that we can do this in predictive control. Another thing is most of this motion cannot be solved with a classical DDP. So you can see here, ICAP robot, it's not able to jump with a DDP. So these small changes in DDP leads to good improvement. Another feature I want to take the opportunity to say that some of the features of Crocoddyl is we use the manifold. So we are like very merry with Pinocchio on that aspect. And that's the reason why we can generate trajectories where with this from fluid motion and that does not violate, does not get into singularity. We don't have yet gain singularity. So we are working the proper manifold. But the concept of feasibility, to be honest, can be extended to solvers where consider other kind of constraints. So here in this follow work, what we do is we are considering torque limits and other limits through penalization, other constraints like the friction cone, and yet we see a surprising improvement, convergence and globalization. And this is also the reason why you saw this video of Taros grasping the bar and doing this Atlantic gymnastic maneuver won't be possible with DDP. So another element of Crocodyle is the content dynamics. So I'm not going to go through the content dynamic of what it means. I hope you get it well with Jostein presentation. But when I say and Jostein say content dynamic, perhaps I mean what we are thinking is about this equation here. What you can see in the first equation is the full dynamics of your system. And in the second block of this equation, the second row, what you can see is an algebraic constraint that basically is telling you that the content should not accelerate. So these are the full dynamics because tau b is basically, it's a compact description, but it contains the torque input of the joint, but also the Coriolis effect term and also the gravitational vector. So this is the full dynamics, but in a compact way. What, as you might know, DDP it's doing forward rollouts to get the new gas, right? When you use the content dynamic, basically you are rolling out, you're getting a new acceleration, this v dot, that is in the constraint manifold. And this leads to improvement in convergence as well. Because this is also helped with the connection of the feedback gain. So you can see this feedback gain as a spring that are pushing your trajectory into a reference. I mean, pushing your system into a reference. This is when the solver is iterating. So that is a good feature, but also another good feature is when we compute the derivative of this. So we are computing the derivative where we are getting the Jacobians of the system dynamics, we're getting Jacobians of the acceleration that are in the constraint manifold. And we don't need to use an equality constraint solver, for instance, that will increase the complexity of the system. There are some good examples, some good words that are doing a very good job, but I still believe that this is much better because you can, this for computing this derivative, what you need to do is something like a short complement, and also you can parallelize this routine, and you don't do this in the recursive recursion. So this also leads with some benefit in terms of computational aspect for computing these trajectories. So Crocoddyl, there are many oncoming features that still are not yet in the repository. Some of the features are we have an efficient method for handling equality and inequality constraints. We're working also in a method that can deal between feasibility and optimality of this problem. So when you cannot optimize, you get you solve the feasible problem. We have some work on differentiable optimal control solvers. and this is related with the codesign project that I'm gonna describe today. We have a optimal control formulation based on inverse dynamics. We had some earlier work on sparse and co-generation of fricative recursions. We are also working on the parallelization of the backward and forward paths in a technical some way. So this is everything about Crocoddyl. So this is, you might think Crocoddyl like your physics engine from your predictive control algorithm. So here I want to present what I call Caracal. So it stands for context phase and rapid model predictive control algorithm. So Caracal, what it's doing, it's basically again assuming set of behavior that has been predefined. It can be also planned by I don't know, mixed integer, or it can come from a deep neural network, whatever. You can think in different ways of doing this, but at the moment we predefine this behavior. So you can see this phase diagram where we know in this 8 phases where a left foot or a right foot will be in contact or will be moving. When the contact, when we are expecting to gain a contact, so think about like the left front between the phase 3 and 4, we are including impulse dynamics, which helps to solve convergence quickly, especially in motion like jumping motions. And in the left side, you can see, the equation of this problem. So basically, what we want to do is to minimize this set of running cost function subject to some contact impulse dynamics that are depending of your predefined behavior. We also pre-describe friction constraint to guarantee the balance of the motion, that the robot will be balanced, the contact placement to achieve the desired behavior, in this case, foot hold location, the joint limits to ensure that it's going to be feasible, and any potential collision avoidance with the environment and with the robot itself. So these are the kind of motion that we can generate. So we can generate any kind of gait. Like this walking gait is actually a fast walking gait because we have 2 legs in a phase that we only to fit on contact. But we can generate, trotting, pacing, jumping gaits. We can also climb more efficiently the stairs that are high and that is easy to reach torque limits. And I will show you some experimental results on that. So, but before that, let me just describe a bit more about the predictive control pipeline. So we have a full dynamics MPC that runs at 50 Hz, although that can run even 3 times faster, but we haven't seen any benefit on that. Just decide to use a, good laptop rather than going from a, more complex CPU. Another thing that you can see in the simulation is a state feedback controller. So the run at 40 Hz. So this state feedback controller is actually a controller computed by the same first principle used for trajectory optimization, because these are, the feedback gains that we compute with DDP. This particular motion, that although might look very aggressive, perhaps not feasible on the real animal, I will argue that is quite feasible because I have reduced intentionally the torque limits of animal 32 for this simulation, 32 Newton meters, which as far as I understand is much lower, not much, but lower to the animal B torque limits. Well, another thing that you can see is how the MPC works. And you can see this shadow posture. This is the target posture of the robot in a specific instant of the predictive control, actually in the terminal state. And you can see how the swing trajectories are outdated. They almost outdated very quickly. And this shows a bit how fast our algorithm converges as well in really few iterations. So these are some experiments that I did around half a year ago. So, but I still put it because I wanted to show you a bit of the tracking without going to more complex motions. So you can see that the ground reaction forces tracking. So where the purple is the current one and the green is the desired contact forces that the MPC is planning. So I also work in different control pipelines, and I'm gonna talk a bit of this. This might be also sort of like interesting for many of you guys. So what we have is a full dynamics MPC. Typically, if you like do like, for example, as many people also like Majid present before me, what you want to do is to have a whole body controller, a TSID algorithm like the one that Andrea present to track instantaneously a set of reference of tasks. These reference typically are CON motion, twin motion, sometimes central momentum, sometimes body orientation, and contact forces, depending on the assumption that you have in your MPC. But we can supply all of this information because we are using the full dynamics of the system. On the other hand, you can have what I call the state feedback controller, what I presented the previous simulation. So the MPC, indeed, it's providing a set of desired state sets, feed-forward torque, but also feedback gains. So what you can see here is the first architecture, the one in the top, is like a real-time motion planning architecture, but in the bottom is a real-time motion control, because now we are not only computing optimal trajectories, but also using from the same first principle that we use for the computing the optimal trajectory, we're computing the optimal local policies. And this indeed leads to different in the robot behavior. So this is a walking gait. In the top video, you can see that the motion of the trunk is quite, let's say, static, not so much pitching angles, but in the bottom it's completely different. You can see that the robot is doing a lot of pitching angle. It looks less intuitive, but this motion is reducing the torque limit. So I think it's an optimal motion. But a part of that, that we might argue is what is the optimal? No. What I wanted to tell you is when you use a whole body controller and you hand tune your gains, you are actually hand tuning a local policy, which is different to the policy computed by the optimal trajectory. So there is some of disagreement in this here, and this brings also motivates why we should use DDP, not also for computational aspect, but also because we can devise motion control architectures that where we don't have this conflict between whole body controllers and full dynamics MPC. Other work that we have been doing that is also a particular feature of Crocoddyl is this control parameterization and higher order integrator. Well, more about control parameterization. But let me tell you a few insights about this. You might see a Runge-Kutta integrator, like performing different computation in several nodes. If you think about the Runge-Kutta 4, it's like you can four chunks like this, but all these are computing one single unit, let's say. That again, because we are using direct classification, can be parallelized, but this is not, there's not a free lunch here, because it's true, you can parallelize this, you can, for the same time horizon, you can have less nodes, but you will have nodes that are larger when you, with larger system dimension. That will increase, of course, the computational time. But there is a point where there's a good trade-off that you can still gain speed on that. And this, in short, depends on the robot that you are using, the dimension of your robot. There's not a unique answer for every robot, but I can tell you that there are some benefits. But the problem that you see is now you have the speed problem that has a longer duration, let's say like 4 times if we are talking about the Runge-Kutta 4. You want not to use, you know, a piecewise constant control on that. So because it won't be that nice to run in a robot. So create a smoother motion. So what we have to do is to introduce the notion of control parameterization. So then we can get optimized instant piecewise constant signals. We optimize some parameter of this polynomial curve, and can be easily done by just applying the chain rule as you can see in this equation. So how you change our optimal control problem? This is the vanilla optimal control.
Carlos?
Yes.
Sorry, I think your time is done. Do you want to wrap up?
Yes, I want to wrap up quickly.
Yeah, it's been 45 minutes now, exactly.
Okay, Okay, sorry for that. So this is, let me try to grab out in 5 minutes. Is that okay?
Sure.
Okay.
Also, yeah, less would also work.
Okay, I will try less. So this is the vanilla optimization problem, and now this is the problem that optimizing the control parameter space, and also this change the way that we control the system, because now we have forward parameters in the parameter state and also feedback gains. And these are some of the video. So what you can see here is an animal climbing the stair. So this is 70 centimeters. As far as I know, this has been not achieved by other teams in the world with the animal B, because I mean, these are high stairs for animal B, easy to reach torque limits. And especially I bring this video because there are many wrong things happening and still the NPC is working on handling. So the animal robot missed three steps, and then it gets this weird posture with a small support region and still finding a solution that keep the torque limits. These are all the videos where you can see the animal jumping 6 times. This might look trivial, but it is not a trivial problem, because you need to land in a specific well posture to be able to do the next jump. And this requires a quite good conversion and efficiency, and also execution, the state feedback control, a good execution. So this would be very difficult to generate with a whole body controller. These are other motions where you can see the animal is jumping, twisting 30 degrees. There are some errors due to a state estimation. State estimation is quite challenging during the flight phases, but still NPC can handle. We can also go over obstacles, over this pallet with multiple jumps. And again, this is possible thanks to the full dynamics and to the use of the state feedback controller as well. Yeah, I think I could stop here. Yeah, I don't have time for talking about the codesign project, but I would like to